So, you've probably heard that quantum computers are going to solve some of the world's biggest problems. But there's always been this huge catch. The quantum information itself is just incredibly fragile. I mean, the real challenge is how do you protect something that can be destroyed by just looking at it the wrong way? Well, today we're diving into what might be the next great leap in solving that problem: dynamic surface codes.
Okay, so here's our game plan. First, we'll get right into the weeds of the quantum noise problem. Then, we'll look at the first big solution, these things called static codes, and why they kind of hit a wall. After that, we'll meet the hero of our story, dynamic circuits. We're going to break down 3 really cool, powerful new solutions, and then we'll tie it all together to see how this puts us on the path to truly fault-tolerant quantum computing.
All right, let's just start with that core challenge. You see, the very thing that makes quantum computers so incredibly powerful, their insane sensitivity, is also their greatest weakness. It's what makes them so unstable.
I love this metaphor. Picture this. You're trying to write a really complex message on the surface of a soap bubble, right? The slightest little breeze, a tiny vibration, and poof, your message is just gone. That is exactly the problem that quantum researchers are up against. The individual quantum bits, the qubits, they're just like those soap bubbles, constantly getting wiped out by any little bit of noise from the environment.
So what's the solution? It's a brilliantly simple idea called quantum error correction, or QEC. Instead of relying on just one of those fragile soap bubble physical qubits, you bundle a whole bunch of them together, and that collective creates a single, super robust, error-corrected logical qubit. It's like we're building a digital safe, that's our logical qubit, to protect the fragile message inside.
Now, the first huge breakthrough in building this quantum safe was something called the static surface code. And listen, it was a massive milestone. It proved error correction wasn't just a fantasy, but as we're about to see, that shield it created was, well, a little too rigid.
So what do we even mean by static here? It basically means the quantum computer runs one single unchanging set of instructions over and over and over again. It's a fixed routine, and its only job is to constantly check for errors and fix them. Think of it like a security guard on patrol who walks the exact same route every single hour, no matter what. The circuit checks for errors, fixes them, and then boom, right back to the start of the same cycle. And you know, that repetition does provide stability. It was the key to proving that QEC could even work in the first place.
But that rigid, repeating pattern, it has some pretty serious drawbacks. Like, what if one of your physical qubits just dies, a dropout? A static code has a really hard time working around that. It also kind of locks you into very specific hardware designs, and it's vulnerable to these really sneaky errors, like something called leakage, where a qubit just jumps out of its assigned energy state. So yeah, that fixed shield, it's got some cracks.
And this is where things get really exciting. To get past the limits of that rigid defense, researchers developed a much smarter, much more adaptable shield, the dynamic circuit.
Okay, check this out, because this visual really nails the core difference. With the static code on the left, the regions that detect errors are like tiles on a floor, a perfect repeating square pattern, always the same. But look at the dynamic code on the right. The pattern of those detecting regions actually changes and alternates with every single cycle. Our guard isn't walking the same route anymore. They're changing it up, which lets them spot problems they would have missed before.
And look, this new flexible approach isn't just some cool idea on a whiteboard. Researchers have already built and tested dynamic circuits that solve very specific, very real problems. Let's take a look at 3 of them right now.
First up, we've got the hexagonal circuit. Now, one of the biggest headaches in building quantum computers is just the physical wiring. Static codes demand really complex connections. This dynamic solution tackles that problem head-on, making the hardware itself way more efficient and, frankly, easier to build.
And this chart just lays it out perfectly. A standard static code, that square lattice, needs each qubit to be connected to 4 of its neighbors, 4 couplers. But by using this dynamic hexagonal circuit, you only need 3. And that might not sound like a huge deal, but dropping from 4 to 3 connections per qubit is a massive simplification in chip design, which can lead to much better performance overall. All right, solution number 2 is the walking circuit. And this one is designed to fight that sneaky leakage error we were just talking about, where qubits decide to just pop out of their computational states and start causing all sorts of problems.
So the trick here is pretty clever. The circuit periodically swaps the roles of the data qubits and the measure qubits that check them. By doing this, it makes sure every qubit gets reset over time. And the result? It's huge. those nasty, lingering correlated errors get smacked down by over an order of magnitude. That is a massive, massive improvement.
And for our third trick, we have the iSWAP circuit. Now this one's a real game changer because it proves you're not stuck using just one kind of quantum gate for error correction. This circuit successfully uses a totally different tool from the toolbox, the iSWAP gate, to get the job done.
And guess what? It totally works. It achieved an error suppression factor of 1.56. Now the key takeaway here isn't just the number, it's that this proves it's possible. It opens the door for engineers to design future quantum chips that are optimized for different, maybe even better kinds of gates. The toolkit just got a whole lot bigger.
Okay, so we've seen these three really cool, specific solutions. But let's zoom out. What's the big picture here? What does this new dynamic toolkit really mean for the future? Well, it's all about paving the road to the ultimate goal, a truly fault-tolerant quantum computer.
You know, there's a line from the research paper that just nails it. It says, dynamic circuits open new avenues for co-designing quantum hardware and error correction protocols. For the first time, the people building the chips and the people writing the error correction software can actually work together, in harmony, instead of being locked into one rigid way of doing things. So let's just recap the huge advantages we've unlocked here. We get way more flexibility in how we design the hardware, we get a bigger menu of quantum gates to choose from, and maybe most importantly, we get the ability to dynamically work around those inevitable broken qubits. All of this is pushing us so much closer to that next holy grail, creating a logical qubit that can finally live long enough to do something truly world-changing.
Look, this shift, going from a rigid static shield to a smart, adaptable, dynamic defense system, it's a profound step forward. It makes the whole idea of building a quantum computer more robust, more flexible, and honestly, just more practical. And that leaves us with the ultimate question. With these smarter defenses getting better and better at protecting quantum information, what are the problems we're finally going to unlock? What challenges in medicine, or new materials, or fundamental science are we about to solve?